This is the Introduction to VLSI Design class, and we will discuss DC and transient response today. Last video, we discussed the transistor theory, which is basically the relation between the current and the voltage in the channel. We had VDS on the x-axis, and we wanted to find the IDS in the y-axis. And we came up with the Shockley model, which is basically have three different regions: the cutoff region, the linear region, and the saturation region. Today, we will focus on the DC and transient response, and we will find that when we say DC response, which is the critical part here, we mean finding the relation between the input voltage and the output voltage of a certain gate. And we will take an inverter as an example. So let's begin. We will talk about the best transistors, the DC response, and we will touch the noise margins. And then we will talk also about the transient response, which is basically not the focus here. We focus more on the DC response. And we will finish with a very critical subject, which is the delay estimation. And we will do it by some methods, and we will focus on the RC delay models as well. So in the bus transistor, we mentioned before that the VDD and ground rails, they are the strongest logic 1 and logic 0. And we also said that the NMOS passes strong 0, but it degrades or weaken the logic 1. This degradation means that the NMOS bus transistor pulls no higher than VDD minus V threshold. Thus, because the NMOS passes strong 0, they are best for a pull-down network. So just to see it here in a figure, if you have those two terminals as input, you consider them as inputs, and you consider this as an output, now we know that this is actually the real input because it passes through the channel. The current passes through the channel. The gate here is only to open or close this transistor, either make it on or off. So what happens is if you have VDD in the gate terminal, which means that the transistor is on, and you also have VDD coming through this terminal, then the output would be VDD taking out from that VDD the V threshold. So it's VDD minus V threshold of the NMOS. Usually V threshold is positive, so the VDD, if we say that this is 5 volt, you take the amount of V threshold, let's say it's 1, so it becomes 4 volts. And we will have examples soon. Now moving to the PMOS. The PMOS passes strong 1, but it degrades or weakens the logic 0. This means that the PMOS passes transistors, or PMOS pass transistor pulls no lower than V threshold of P. Since PMOS passes strong 1, then they are best for pull-up network. And this is what we mentioned when we try to memorize the inverter. In the pull-up, you have the PMOS close to the VDD. In the pull-down, you have the NMOS close to the ground. One solution that we mentioned before, that transmission gates are needed to pass both zeros and ones. But before we move to the next slide, let's check the PMOS again. If you have the PMOS on, being applying 0 volt in the gate, and in this terminal you have also 0 volt, then at the output, because now it's 0, it's degraded through the PMOS, it will be not exactly zero, it's slightly more than zero, which is basically zero plus the absolute value of the V threshold of the P. Notice that the V threshold of the P is a negative value, so if you take the absolute value, it's going to be positive. Now, to understand this better, we will formulate it mathematically this way. So in base transistor, finding one terminal voltage, if the other two terminals are known, is the target here. So let's say that in the NMOS, you have the input and the V gate. These are your known values, and you want to find the voltage at the output. Similarly for the PMOS. So in the NMOS, we know that it passes the zero better. You have two cases. One case for strong output and the other case for a degraded output. How did it differentiate between these two cases? You compare the voltage at the input, which is in this terminal. You compare it with the voltage at the gate minus V threshold of N. So basically what you do is you take out, you have to put this in, or you do this calculation in your head without writing. So you say VG and you take out the V threshold of N from it. And then you compare these two values, this value with this value. If the V input is less, so this one is less than this one, then you have a strong case output, which means that the V output is equal to the V at the voltage at the input without degradation. So you'll have the same the value of the voltage in the output as well. Now, in the second case, you compare again. Now, if this is the larger value and this is the lesser value, then the V output is going to be equal VG minus V threshold of N, which means that the output is actually degraded. Basically, you can think about both cases at the same time by comparing those two, and whoever is having the lesser value is the one that is going to be generated in the V output. Now, for the PMOS, it's the other way around. Remember that the PMOS passes one better. Again, you compare those two values. You have VG, but now you add the value of the V threshold of P, and this is going to be the absolute value. So it's not negative. And you add the VG to that value. And then you compare those two quantities. Whoever is larger is the one going to show up in the output. So if VI is larger than the VG plus V threshold of P, the absolute value of it, then the VI is the one that's going to show up in the output, and we have a strong output. If not, then we have a degraded output, which means that it's more than VG. It's VG plus V threshold of P. Just remember that when we say logic 1, if we say that VDD is 5 volt, this means it's 5 volt. And we have logic 0. And let's say it's 0 volt. So what happened is the degraded value, let's say that the V threshold of N is equal to the V threshold of P, the absolute value of it, and let's say it's 1 volt. So what happened when the NMOS is on, this means you have the VG at 5 volt, at 5 volt. So let's say you have also 5 volt in the input. So 5 volt here, 5 volt minus 1, which is the V threshold, is 4 volt. So you take the lesser value, which is 4 volt, and it's going to be in the output. This means that the output is degraded from 5 volt, and it is now 4 volt. It's going down. So the degradation in the NMOS, it's actually a lesser value than the amount of the VDD. In our example, it's 4 volts. If we say that the VDD is 5 volts. Now, for logic 0, the degradation means that you are basically increasing the value of the 0 volt because the PMOS works when the VG is equal to 0. So when you have, let's say that you have also in the input 0, so you have 0 here, and the VG plus the V threshold of P, the absolute value of it, I mean, is equal to 1. So you compare 1 to 0, and the winner is the maximum value in the PMOS, which is going to be 1. So the degradation here is actually an increased value of the voltage, which is 1 volt here. So that being said, all these rules, all of what we've discussed, they are applied only or if and only if the transistor is on. If the transistor is off, nothing will show up in the V output. If it is on now, then once you are sure it's on, then you can apply these rules. To understand this better, we will give you some examples, like very simple examples, and then we will give you like some hints and some exercises to understand what's going on. So let's say that here the VDD is 5 volt, and the V threshold of N is equal to the V threshold, or the absolute value of the V threshold of P, which is equal to 0.5 volt. Now, in the NMOS case, which we said that it passes the 0 better, let's have case 1. In this example, we have 5 volt here, we have 2 volt here. So you take the V threshold, always you take it out, or you add it in the gate. You take it out from the NMOS, and you add it, the V threshold of the P, the absolute value of the V threshold of B, you add it to the PMOS. You always work with the gate. The V threshold works with the gate. So 5 minus 0.5, now we have here 4.5, and you compare this value to the value of 2 volt, and you know that you get the lesser value in the NMOS, so you have 2. Now for the other case, if we say that you have 2 and 2, so you take out now the threshold value from here, it becomes 1.5, and you compare 1.5 with this 2, so the 1.5 is the one that's going to show up in the output. For the PMOS, let's say you have 2 and 5. Now 2, now because it's PMOS, you add actually the absolute value of the threshold V threshold of P, which is 0.5 volt, as we said. They are both the same in this example. So you take 2 and you add to it half a voltage, so it becomes 2.5. It becomes 2.5, and now you compare 2.5 to 5 voltage, and you take the maximum voltage in the PMOS, which is 5. For this one, you have 2, and you add to it the V threshold, absolute value of the V threshold of P, which is going to be 2.5. And now you compare this one to 2, and you take the maximum, and the maximum now is the one in the gate, which is 2.5. You can see that you have strong value here. You have strong value here. The 5 goes out to 5. And here you have degradation. And here you have also degradation. Notice that the amount of degradation is reduced here. And now it's increased in this case in the PMOS. So now here it's degraded. And here is also. Okay. Now, when we talked about the first slide, we say that if you have VDD and VDD, you take out the threshold voltage from the gate, and you came up with VDD minus V threshold in the NMOS. In the PMOS, you will add the absolute value of the V threshold of P, because you have 0 here and you 0 here, so you add this in the output. This is if you have a single pass transistor. But what if you have multiple transistors connected in a certain way? We have 2 examples here to show some of the ideas to you. If we have a series NMOS transistors this way, so what happens, you compare VDD with VDD, and you take out the V threshold of N from the VDD at the gate. You compare these 2 values, and you know that this is the lesser value, so it comes up in the output. Now you compare those 2. Remember, you take out the V threshold always from the gate. So VDD minus V threshold of N, you compare this value to this value, and you see that they are equal. So we say that it's VDD minus V threshold here. And now you know what's going on. This is repeated no matter how many transistors you are adding, because you always will compare this value to VDD minus V threshold of N. And then you come up again with VDD minus V threshold and so on. Now, in the other case, if they are connected this way, where this terminal is connected to the gate of the next transistor, notice that this terminal is connected to this one, and this one is connected to this one, and so on. So every source is connected to the drain. But here we have this terminal connected to the gate. So what happened here is, again, you apply the same rule. You have VDD, and you have VDD over here, minus V threshold of N. You take the lesser value since it's inmost, and you have VDD minus V threshold over here. Now, this VDD minus V threshold, now it's on the gate, and you compare it to this value. So you take another V threshold of N. So now you compare this whole value with this one, and you know that this is the lesser value, which is VDD minus twice the V threshold. So you will have worsened degradation every time if you keep connecting this one. So now let's combine everything together in an example. And this exercise, you should label the voltage swing, which is the maximum and the minimum voltage at each node. And you have 1, 2, 3, 4, 5 nodes. Given that the input to the system vary between two states, you have two states, state 1 and state 2. In state 1, A is 2.5 volt and B is 0 volt. So let's put these or plug them in the figure. So you have here 2.5 volt and here you have 0 volt. This is the first state. And you have some assumption. Basically, you should know that the V threshold value, the V threshold is equal to 0.5 for both the N and P, and the VDD is 2.5 volts, unless it's marked otherwise. Like here, it's 1.6 volts. Here and also here, it should be 2.5 volts. So let me write it in another color. Say it's black, so this is 2.5 volts. If you see this sample, you know that this is the VD, 2.5 V, 2.5 voltage. And here you have 0 voltage, which is the ground, similarly here and here. Now, let's go back again, and we keep calculating. We keep calculating from the input all the way to the output. But first, before you do anything, make sure of what is the status of the transistor themselves. Are they on or off? So in this case, the transistor is on. In this case, you have 0 volt in the inmost transistor, which means that this transistor is off. Similarly here, this transistor is off. The gate here is connected to the gate over there. Now for this transistor, since it's connected to 0 volt, this transistor is on. And if you looked at this transistor, you looked at the gate, you didn't calculate it yet. So let's wait for this value to here to decide its fate. So let's go on, or let's go back to first node. So here you compare those two. Remember, where is the gate? The gate is here. So you take the V threshold from there. So 2.5 minus 0.5 is 2. You compare 2 to 1.6, and you know that the minimum value here is the 1.6. This is for state 1. Keep continuing. So you have 1.6 here. Now it's in this terminal, and the gate, you take 0.5 out of it. So it's 2 voltage. 2 volt compared to 1.6 volt. This means that you will have again the minimum value, which is 1.6. And you will have the same exact scenario in this transistor. You can figure this out from the previous example of the previous slide. So you have also again 1.6 over here. You can also calculate, it's very simple calculation. 2.5 minus 5 is 2 compared to 1.6. 1.6 is the winner because it's the lesser value. Now the 1.6 is the value at the gate. Now we can decide the fate of this transistor. Since it's not 0 volt, we will assume that this transistor is on. So what happens now, the gate value is 1.6. We take 0.5 out of it. So it becomes 1.1 compared to 2.5. Then the winner here is 1.1. Now the 1.1, and you have now another type of transistor. Be careful. This is a PMOS transistor. So at the gate, you have 0 voltage. You add to it 0.5. And you take the maximum value. So 0.5 and 1.1, the maximum value is 1.1. So you keep calculating this way, no matter what is the circuit. Now let's have the other state. We'll change the color. Let's say it's green color. So here in this state, you have A is equal to 0 volt and B is equal to 2.5. So in the A, you have 0, and here you have 2.5 volt. So in this case, again, remember, check the transistors. Are they on or off at in this state, or in this voltage swing? So in the 0 volt, you have, this is off, this one is on, and this one is on. This one, we will check it later. And this one is always on, because it has 0 volt in the gate of a PMOS. So since this is an off, you can cut it off completely from the circuit. So you know that now you have 2.5 and you have 0 voltage over here. Basically, this is NMOS and the 0 is a strong value, so it goes as a 0. But still, you can calculate it. You have 2.5, you take out 5 from it, so it becomes 2 volt compared to 0 volt. You take the lesser value, which is going to be 0 volt. Again, the 0 volt in an NMOS, it's going to be strong. It's going to be strong here. And because it's a 0 in the NMOS, now this transistor is off. So we can calculate this node coming out or coming from this bar, which is actually, you have 0 volt here, and you have 2.5. The 2.5 is also connected here. So the 2.5, you take 5 out, 0.5 out of it, so it becomes 2 volt compared to the 0 volt. So you will end up with 0 over here. Now the 0 volt at this node, and you have 0 volt at the gate of a PMOS. So you add the V threshold of P, which is 0.5. So you compare 0.5 to 0. Now you get the maximum value, which is the 0.5. And this is what you will end up in the output. So I hope this exercise shows you what to do or how to deal with the voltages when you have pass transistor, and when exactly it's going to be strong values, when it's going to be degraded, and what does that mean? You should already know it from these few slides. The values that we just got, they are here in this next slide. Now, after discussing the pass transistors voltages at different terminals, we will talk about the DC response. So what do we mean by DC response? It's actually the relation between the voltage at the input versus the voltage at the output of a certain gate. And every book actually in VLSI design, they take the simplest gate, which is the inverter, which means when the voltage at the inputs is 0, since it's an inverter, the output would be VDD. Remember, if it is 0, then this is going to be 1, which is VDD. If the input is VDD, meaning if this is 1, then your output is going to be 0. This is how the inverter works. There is the amount of voltage itself depends on many things like the transistor size and the current and so on. And we have currents going through the PMOS and the NMOS based on its saturation. So let's look at them again. If you have 0, then this is on and this is off, which means that this output node it's actually charged by the voltage. And it is charged by the voltage by having a current going to this direction. We call it the IDS. IDS, the one that you know from the transistor theory, it's IDS, but now we add P for it to indicate that it's a PMOS. Now, the output also is logic 1 since it's an inverter, and the connection is very clear. The VDD is coming out in the V out. If you have the other case where you have one here, one in the input, the output is going to be 0 because this one is going to be off, since you have one here, and this transistor, the NMOS, is going to be on, which means that this node is discharging its value to the ground. So the output is going to be 0, and you have a current running through the NMOS that is the IDSN. So we know the transistor operations. So the current, this current, whether it's IDSB or the IDSN, depends on the region of the transistor behavior. So we will try to figure out the relation between the input, the voltage in the input and the output of the NMOS and the PMOS from the equation that we already know before, which is the Shockley model, where you have cutoff, linear, and saturation regions. To understand this better, we will just remind you of what we've said before. In the NMOS, we have a cutoff, linear, and saturation, and these are the conditions for this. The condition for the cutoff, if the VGSN minus V threshold is less than 0, or you could rewrite it this way, if VGSN less than the V threshold of the N, then you have a cutoff. If it is larger, if the VGSN is larger than the V threshold of N, then you are either in the linear or in the saturated region based on the relation between VDSN and the VGSN minus V threshold. Now, if the VDSN is less than this amount, then you are in the linear. If it is larger than this amount, then you are in the saturation region. And we discussed this before. You can go to the previous video for more details. Now, what happens in the NMOS operation? Here we have the input voltage and the output voltage. And we know from the equation that is written, or the inequalities that are written in black, that the voltage difference actually between the input and the ground is the VGSN. So we would say that the VGSN is equal to the voltage difference between the VN minus the ground, which is the 0 value. So since it's 0, it's not written. Similarly, in the output, you have the relation here between the output and the ground, and the VDSN is equal to the V out. This is for the NMOS operation. So notice that there is a very good assignment here, where the VGSN is actually the V input, and the VDSN, which is here, is actually the V output. If we want to do this for the PMOS operation, you can compare between the slide. I will go back and forth quickly so you can compare. Notice the inequalities here. Also, the value of the V threshold of the P. If you compare the N to the P, you can see that the inequalities are the other way around. Now, what happens is, because you have the PMOS operation, this is on. So what happens is, now the VGSP is the voltage difference between the input and the VDD. So it's actually VN minus VDD. The VGSP is VN minus VDD, because now you have these two nodes. Similarly, the VDSP is actually the output minus VD. So if you compare this to what we discussed in the NMOS here, it's actually minus 0 and minus 0 over here, but we don't write it down. In the BMOS, it's minus VDD and minus VDD. And now, to compile everything together, now we know the regions, the cutoff, the linear, and the saturation regions, and what are the conditions based on the value of the Vin and the Vout. Basically, we just take out the VGS, whether it's in and B, and we plug in the input and the output based on the equations that we just highlighted. This one for the PMOS, or these two for the PMOS, and these two for the NMOS. If we take out the VGSN, you have the input. If we take the VDSN, then you have the V output. Similarly, here with the addition of minus VDD in the PMOS transistor. Now we can draw the one that we already know, which is the relation, the transistor theory, the relation between VDS and IDS. In the NMOS, which is the green lines, and we've shown this before, and the PMOS is actually in the third quarter. This is the first, this is the second, this is the third quarter, and this is the fourth quarter. So it's in the third quarter. And notice that the VDSP is a negative value, and also the IDSP is negative value. And we also need to make sure that the PMOS is wider than the NMOS, such that both betas are equal. And we know that the mobility of the N is equal twice the mobility of the P, and we can equalize the betas if we make the width of the B more than the width of the N. And we will come to that in more detail in one of the coming slides. This is actually very critical for the CMOS design, to make the PMOS. If you have a CMOS design, the PMOS should be wider than the NMOS. If you want the relation between the VDS and the IDS and the NMOS and the PMOS to look more like this one, it's kind of symmetrical around the origin point, which even looks nice. So what happens now is we will try to put them in the same quarter by applying the absolute value for the VDSP and the IDSP. So if we have the absolute value here and here, what will happen to this part here is that we will flip it over here in the second quarter if we make the current positive. So if we take the absolute value, this is what happens. It will be flipped in the other way around in the second quarter. And then if you flip this value, it will be shifted or pulled in the right direction to this quarter. Basically, as the final result or the conclusion from all this discussion, this is what we will end up with, where you have the transistor theory for the NMOS and the PMOS in the same quarter, which is the first quarter. So why do we do this? Now we have the relation between the V output, which is the VDS, and now you have V output. Remember, our target is to get the DC response, which is the relation between the input and the output. Now we have the V output here, and we have the currents in the y-axis for IDSN and IDSP. We want to get rid of them somehow. And we have the inputs with many, actually, curves based on the value of the VGS. The VGS is basically the input. That's what we agreed upon in the previous few slides. So what we want to do is for a given Vn, notice now you have Vn here, which is the VGS of the NMOS or the PMOS, the VGS minus VDD in this case, but it's there. So for a given Vn, you plot the IDSN and the IDSB versus the V output. And the V output must be where currents are equal in both graphs, meaning the green and the blue graphs. So just to recall what we've learned, that there is a current here indicated by the blue line, it's the IDSP, and it should be in one of these the curves based on the input, based on the value in the input. Similarly, we have another current here, the IDSN, and it should be in one of these curves based on the input again of the green curve. So we will do this step by step. For the NMOS and the PMOS, we will see its behavior when this input is equal to 0. When this input is equal to 0, you are actually having this curve, which is the VN0, which is basically, it's not even shown because it's right on the black line of the x-axis. And the other curve that is working for the PMOS is the one shown here, which is this one. Now, the intersection point between those two curves is right there, where the NMOS is actually in the cutoff region, and the PMOS, and you can see here that it's in the linear region. Now let's increase the input voltage a little bit. So we increase it to 20% of the VDD, or 0.2 VDD. So what happens now is we are moving in a lower curve in the PMOS, and it's in the next curve of the NMOS, the green curve. So here we have the NMOS still in the cutoff and the PMOS in the linear. Let's increase it a little bit more. So let's say let's take 40%. Now it's very clear in this point that it is for the NMOS, it's in the saturation region, and for the PMOS, it's in the linear region. And we are again dropping to the next curve of the PMOS, and we are moving up in the next curve of the NMOS. Increasing again the VN to 60%. So now there is a big jump from this region here all the way to this region. So now the intersection point is in the PMOS, it's the saturation, and the NMOS, it's in the linear. Increasing a little bit more, 80%. So now you have the NMOS in the linear and the PMOS in the cutoff. And if you take it 100% VDD or simply VDD, now the curve of the PMOS transistor is exactly on the axis, and it's in the cutoff region, and in the NMOS, it's in the linear region. So now we can see that there is a certain relation between the output and the input. Let's look at it again. Remember, we are talking about the inverter. We are talking about the inverter. We take the inverter as our example circuit. So going back to the first slide, when you have the V input is equal to 0, that's the input. The output is supposed to be VDD because it's an inverter. And this is actually right. The output is VDD. Now, if you increase the inputs a little bit, which is only 20% or even 40%, you can see that the red operating point is still close to the VDD, which you can consider logic 1. Now, if you increase the input to 60%, now it's closer to the logic 1 in the input. So in the output, it's closer to the ground, which is based on the inverter. The inverter, if you have logic 1 in the input, then it's logic 0 in the output. Again, if you increase it to 80%, it's even getting closer to the ground or logic 0. And if it is 100%, it's exactly on the value 0 volts. So it's working as we expected. And we kind of having this relation between the input and the output, and we can compile everything together in this graph this way. So you can see that you have 6 points or six operation points, 3 points over here close to the VDD and 3 points over here close to the ground. If you looked at the input values that we have chosen, we chosen 0, 20%, 40%, 60%, 80% and 100%. But we didn't choose 50%, because at the point 50%, you will be in a certain place. And to show you this even better, let's look at it in another graph, which is the DC transfer curve. So we can get the equivalent of this curve over here by having the different operation points of the PMOS and the NMOS at the same time. So now you have the V input here in the x-axis, which is white. This is what actually we want to find the DC response. And you have the voltage at the output in the y-axis. And now you have these regions, A, B, C, D, and E. Now let's look at our points, the 6 points that we found out. You would say that this one is 0%, this one is 20%, and both of them in region A. Region A is when the input is between 0 and the V threshold of N. And in this region, the NMOS is actually in the cutoff and the PMOS in the linear. And we've mentioned this. Now in the next region, P, which is if you increase the voltage more than the V threshold of N, now you are getting away from the cutoff of the NMOS to VDD divided by 2. And actually, not exactly at the point, you are approaching the point from the left. So in this region, you have, or I mean region B, we have the operating point, which is at 40%, which is still here. You can consider it VDD, but the NMOS in this region is actually in the saturation and the PMOS in the lean. Now, jumping to, let's discuss C later. Jumping to region D, we have the operating point 60%, which is between VDD divided by 2, not exactly the point. It's approaching the point from the right to the VDD plus V threshold of P. So in this region, we have what we call the D region, where you have the NMOS now is linear and the PMOS in the saturation. And the last 2 points, the 80% and the 100 in region E, where this region between VDD plus V threshold of P and VDD, and the region E, the NMOS is actually linear, and the PMOS is in the cutoff region. Now you can see that for region A, B, D, and E, we have example when we have operating points in our case. Now the dangerous part is region C. And this is when exactly your input is VDD divided by 2. In that case, actually you don't know exactly what's the voltage at the output. This might be this one or this one or this one. So it's an unknown value, or what we call a dangerous region. Or we can say X, or don't care. And this is what we don't want. We don't want in the input the value to be VDD divided by 2. It's not even at this region, it's not that good. But for these operating points, 0, 20%, and 40%, you can see that the 0 and 20%, they are fairly good. But the 40%, yeah, we accept it, but it's not that good. There is a degradation. Similarly here, the 60%, we would accept it, but we don't really like it. It would be nice if we have the operating points all the time between the VDD and the Z. The thing that I just discussed with you is actually summarized in this table, where you have the regions A, B, C, D, and E, the NMOS and the PMOS operating modes, which is like in A, it's cut off for the NMOS, PMOS, and linear. You can continue for the other regions. The inputs which is the period at the x-axis, is from 0 to V threshold of n. Here it's from V threshold n to VDD divided by 2. And notice that it's a parenthesis here, so we don't include the VDD divided by 2. Similarly, this is the next region and the next region, and they are indicated over. The region C, which is actually this vertical line, is when you have exactly VDD divided by 2. So what happened in the output here, it's VDD, which is logic 1. Here in region B, all of the region B, it's actually larger than VDD divided by 2. We mean that the output is larger than VDD divided by 2. So the output could be anywhere here. If the VDD divided by 2 is here, if VDD divided by 2 at this point, then this is larger. This region here in the curve, it's larger than VDD divided by 2. Now for region D and E, you can see that the region D, you can there, it's actually in D, in the region D, it's less than VDD divided by 2, which we consider it's closer to 0. And if you have it in the region E, then the output is exactly 0. Now here in the region that we don't like much, when both the NMOS and the PMOS in the saturation region, if they are both in the saturation region, it's actually a fight between the two transistors. So you are charging and discharging at the same time. You are charging the output and discharging the output at the same time. So you're not sure what's the value at the output. Is it really high, really low? You are somewhere. So it's unknown. So that's what we say. Either you say it's equal to X or it's dropping sharp. Now, all what the discussion that we had really important assumption, which is that the beta of the N is equal to the beta of the P. And we did that by increasing the width of the PMOS. So the ratio would be 1 to 2. We make the ratio this way because we know that the mobility of the N is twice the mobility of the P. So if we increase the width of the PMOS, then you will be equalizing the value of the betas. Now, what if they are not equal to each other? They are not equal. If beta B, this is what we call the beta ratio. If beta B is divided by beta and not equal to 1, then you have what we call a skewed gate. And you can look at it. This curve here is the one where we have the beta is equal to 1, where beta B is equal to beta N, which is the one that we discussed and the one that looks nice. However, if you increase the ratio, which is for this example 2 or more than 2, we have 2 and we have 10. Now the beta B is larger than the beta N. And what happens is that it's like you are pulling the central curve at this direction. You are pulling the center curve at this direction. If the beta B divided by the beta N is less than 1, for example, here it's 0.5, and here it's 0.1, then you are pulling the curve in this direction. And there is in some results that comes from this pull, whether it is on the left or the right. So to understand better, let's discuss the noise margins. Let's say you have very simple 2 circuits, inverter followed by an inverter. The output of this inverter, like given by certain output characteristic, is fed to the next circuit, which is this inverter as an input. And it also have input characteristic. We could say the same thing if we say that this first gate is driving this gate. So what happens here, in the output characteristic, we will be more restrictive at this point. Just when you have the output getting out from this inverter. So what we say that we will accept the logical high only for this range. And we will accept logic low only for this range. You can see that we are very, very restrictive here. But in this point at the input, we would say that you have like the restriction are taken away. You are more relaxed. So you have, this is the logic high or the logic 1 range, which is bigger or actually very big compared to this one. And this is the logic low. Why we are giving more flexibility at this point and more restriction in this point? Because we have no idea what will happen when the current is moving through this wire. Maybe there will be noise, other effects, secondary effects like coupling and other things. So since you are just getting out from here, let's put more restriction to make sure that what's come out is really good in terms of logic 0 and logic 1. And now if there is some sort of noise and problems along the line, at the input of the next circuit, you have given more flexibility in the logic high and logical low to be accepted as input in the next circuit. This is the intuition. So from this discussion, we have, let's look in the middle region here. If we say this is the VDD and this is the ground, here you have what we call VOH, and here we say VOL. O, this O is for the output, and the H for high, the L for low. Similarly, in this one, if we looked closer to the input, here we call it VIH, the I for the input, and because it's high, and this one VIL, the I again for the input, and the L for the low version. Now, if you take this range, basically you are subtracting a VIH from the VOH, then you have the noise margin at the high, and you also do the same thing, and you have the noise margin at the low. From the looks of it, they are the same. They are equal to each other. And this is only if you have the beta ratio equal to 1. Meaning the beta at the end is equal to the beta at the B. So what will happen if that's not the case? And we discussed this in the next slide. If it's not the case, let's say that you have beta B is larger than beta N. So it's more than 1. So it was pulled from the center in this direction. What happens is, comparing these values, you can see you have a certain slopes here at this point and this point because of this pulling. And now you have a VOH over here and the VOL is over here. You can see compared from 0 to VOL is very small. And here it's like compared to that part, it's kind of large. Again, we do the same for the x-axis. This is for the y-axis. For the x-axis, you have the VIL is all the way over there. So you have big value over here. And the VIH is also over here, which is like a good amount, but still the VIL is much larger than this value. Now, where is the noise margins? Where is the noise margin? This is what we care about. And this is what we said in the previous slides, that they are equal if the beta are the same. Now we change the beta and we pulled it to the right. Where are the noise margins? You could simply say that the difference between the output at the high with the input at the high, this is the noise margin at the high. Indicated, but what we discussed before is the VOH minus VIH. So VOH minus VIH. And you can see that the value of the VOH is quite large here. If you take this and you subtract the VIH from this part, you will end up with something kind of small value. And the noise margin at the high. Now, the noise margin in the low is the VO low minus the VI low, which is basically the VO low. Let me change the color so to show it clearly. This is the VO low. This range here is very short. And the VI low is actually this region over here, indicated, but we just discussed here, which is the VI low. Sorry, it's the VI low subtracted from the VO low, so it's the other way around. And you have actually quite a good value. This is the VI low minus the VO. So the VI low is kind of large compared to this one. So you have a very good noise margin in the low compared to the high if you pull the graph to this direction. Now, after we discuss how to find the DC response, which is the relation between the output, the input, and the voltage at the input and the voltage at the output, we also see what will happen when you have the different beta ratio. Now we will move to the transient response. We won't spend that much time on this. It's not the focus in this class, but the transient response is actually to compare it to DC. The DC analysis tells us the V output if the V input is constant for a long period of time. The transient analysis tells us what is the relation between the input and the output over time. So as the input is changing, what will happen to the output? And it's required solving differential equation. If you work in the time domain, you can switch to frequency domain and you make the differentiation and the integration, multiplication and division. But this is out of the scope of this class. However, the input is usually considered to be a step or a ramp. Now, if you study control courses or signal and system courses, you know what do we mean by step and a ramp input. For example, this is now the black line here, or the black waveform is the input, and we have kind of a square waveform this way. And what happens to the output? Again, we still have the inverter. We still have the inverter. If the input is this way, then the output would be flipped, but with a certain delay. You can see that the output now is pushed in the right direction. So what do we mean by step? To model this mathematically, the input, V input over the certain time is equal to the unit step shifted by amount T0 multiplied by VDD. And now it's this blue curve. So if the rising happens at 0 over here, then we call it U of T. Exactly U of T. But since there is a shift amount, we can get it, it's indicated by T0, then it's UT minus T0 multiplied by VDD. This is the input. So anything before T0 is equal to 0, the input would equal to 0. And after T0, the input is going to be equal to VDD, indicated by VDD here in this equation. Now, what will happen to the output? Again, this is the inversion. If we make the input the blue curve, the output can't be just exactly the opposite. Because what happens when you have zero here, and then you move to one, or let me draw it this way. When you have zero, and then you move to one at t0, what happens in the output, since you have zero at the beginning, it means, and this zero was there for a very long time, then the output is actually one. Now, when this jump happens to the input, the output will start losing its value over time because it's connected to the ground. Since now the input is one, the output should be zero. It's actually connected to the ground, and you are discharging its value slowly until you reach to zero. And this is what we mean by the DC or the transient response. This is what happens in this amount of time. But after a while, when the output settle down, the output will reach to zero and stay zero until you change the input again. How to calculate the V output? Now the V output, if T is less than T0, which is in this region, the output is one, since the input is zero for a very long time. But if the T is in this region, right when you change the input, then it's the dominating equation is the relation between the input, between the current and the voltage, given that you have a certain capacitive load at the output that you need to discharge in this case. So the derivative of the voltage, because the voltage is changing over time, it's losing its value from the capacitor. The chargings or the charges that are there, they are actually discharged to the ground. So they are losing their value over time. So dV out of T over dt, which is the first derivative of the output, is equal to the amount of current. Depends on the current. If the current is high, then you discharge faster. If not, then you have a certain amount. So it's actually IDSN of T divided by the amount of the capacitance. If you have large capacitance, then the derivative would be, if this value is high, then this was going to be low and vice versa. So this sign, the negative sign here, it means that you are actually discharged. You are discharged. If you are charging, I can give you another example where you can be charging this output, then you won't have a negative charge. Now, what about the IDSN and the V output here? You have the IDSN here, this current. The V output is the V output that we are interested on. How to calculate them? Again, you have the Shockley model, where you have a cutoff, linear, and the saturation region. This is the cutoff, this is the saturation, and this is the limit. The only thing that changed here is that the VDSN, or the VDSN that was here and here and here and here, we take them out and we replace them by the V output. And you could draw this by looking at the functions, and we gave example in the previous video. Now, as a simulated inverter delay, solving differential equation by hand is kind of too hard. So that's the first way to get the transient response, is solve this equation, solve this mathematical model. The second way of doing this is using a simulator. One example is the SPICE simulator with so many versions of it. There is SPICE, there is LT SPICE, and many others. So the SPICE simulator solves the equation actually numerically. So you get a model, something like this. But the simulation takes time to write, and maybe it's not the real case, because the one that is really close to the real life is the mathematical. So here, the input, if the input is going this way, then the output is going this way, considering a very slight amount of delay. Now, these delays here, we have TBDF and we have TBDR, and they are generated by this simulator. So to understand them better, we will define them. So if we came across them later in any chapter, we know what these values mean. So we will have the delay definitions. We have the TP shown in many items, TBDR, TBDF, TBD. P here means propagation. The opposite of propagation is the C, which is contamination. Basically, to differentiate between those two, let's say you have a multiplexer, for example, and you have 2-to-1 multiplexer with one selection. So let's the selection be S, and now and those two inputs, one input is simply an inversion of the DZ. The other one has like a very long series of gates. Let's say you have and you have and here, and you have XOR, and you have also an OR, for example, and you have multiple inputs here, 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 and here. Now you know that this output could have a short time to be generated, the D0, and let's say that this is the D1. The D0 to show up in the output after you do the functionality in this path, it will take a shorter time compared to the other path. So we have a short delay here and a long delay here. The short delay indicated by the contamination part in every of these times. The long delay is indicated by the propagation in every one of these delays. So let's take every one of them and check how do we find it. The TBDR is, the BD means propagation delay. So the D, when you see it everywhere, it means delay. But here we have R, so it's rising. The TBDR, the rising propagation delay. And we have the TBDF, the time of the propagation delay in the falling, or the falling propagation delay. If you have, this is the input and this is the output, you calculate 50% of the rising of the input, 50% of the falling of the output. And from this point to this point, you have to the TBDF, which is this one. This is the falling propagation delay. Notice that the falling is indicated by the output. The output is the one that is falling and is the one that we are interested on when we find the delay. This is why we call it fall. Similarly here, this is 50% in the input, 50% in the output, and the rising of the output happens with this delay, the rising propagation delay of the output. So it's from, as indicated again here in these sentences, this is exactly what we described. Now to find the propagation delay of the circuit, being an inverter in our example, or any gate, if you have the simulation values here, you can find the propagation delay using many methods. One of the simplest methods is if you average those 2 times. TBDR plus TBDF divided by 2, you find the propagation delay. Now, if you do the same thing that we discussed here for the contamination, is exactly the same. The only thing is now you have the shorter delay. It's not drawn here. If you want to draw it, you would say, okay, I have 2 output curves. This is the output. If I choose, for example, D0, sorry, D1, which is the long time, D0 is shorter than this. So it's something like this. It's falling down earlier and it's rising also early. Something like this. So in that case, the 50% point is going to be here, and the 50% is going to be here, and from here to there, and from here slightly better. It's kind of hard to draw using the tools that I'm having. So here, this is the CDF, and this is the CDR. As you can see, it's shorter. Compare this one to this one, it's shorter because it's contamination delay. It should be faster. Similarly, if you compare this one to this one. If you want to find the contamination delay, you can take the average between those two delays. Now, for the rise time and the fall time, now the TR and the TF, this is indicated by TF and TR here in this graph, is actually from the TR from the output crossing the 20% VDD to the 80% VDD. So from 80% to 20%. This is the falling time. For the rising, it's from here to there. Notice that the TF and the TR, we worry only about the output. We don't even look at the curve of the input. That's the difference between them and the propagation delay. What we are interested on in this course is the propagation and the contamination delays. These one, they are important, but for other subjects, maybe we will reach some part here and there talking about the rise time and fall time. But for the contamination and the propagation, this is going to be the focus, and we will talk about them in detail, starting from the next slide, which is one of the very important subjects that we want to discuss in this class. Remember, we said that what we want to discuss is how to design good or better circuits. Now, to find out are they good or better, to compare different designs with the same functionality, for example, then you need some tools that could help you find out these matrix. One of them is doing the delay estimation. To do the delay estimation, we would say that the propagation delay is simply equal to the resistance multiplied by the capacitance. This is called the RC delay model to estimate the delay. And C is the total capacitance on the output node, because we are interested on the output. And we also find the effective resistance throughout the model. If we found the total R and the total C, we multiply them by each other, then now you have good estimation for the propagation delay. Now, again, this is just an estimation. And to show this, if you looked at the next slide here, this is to compare the Shockley model, which is the most accurate one, using the mathematical model. This is the blue line. Now, if we do this simulation using SPICE tool, this is the black line. It's very close to the blue line. If we do this simple delay estimation using the RC model, we had the dotted line. Yes, there is a slight difference. You can see that there is a difference between the blue line and the dotted black line. However, this is good estimation, still a good estimation. So, and now we will try to calculate the resistance and also the capacitance. And from after finding the resistance and the capacitance, we will try to give you certain examples to find out the delay to give you good experience in finding this RC delay models for different circuits. So the effective resistance, the Shockley model have limited that. It's not accurate enough. And we can't actually, we want something very simple. We don't want something that takes a lot of time. So we could replace the IDS, VDS, GSS with the effective resistance R and just simply apply the Ohm's law, which is basically V is equal to IR, or the IDS is equal to VDS divided by R. So the how to find the value of R in Ohm, how to find this value or the resistance value. Remember, you can do the CMOS design and you have couple of transistors. For example, if you have two NAND circuit, you have couple of transistors in the pull down, couple of transistors in the pull up. So in total, you have 4 transistors. How to find the resistance of each one of them? That's what you should think about. Similarly, how to find the capacitance for the whole circuit. So for the capacitance, we actually talked about this, and we said that we have the gate capacitance, we have the diffusion capacitance. The gate capacitance is equal to the diffusion capacitance at the source or the drain, which will be some given for a certain generation. So if you say it's a 0.6 micrometer generation, which is kind of an old generation, you have the capacitance 2 femtofarad per micrometer, which means to get the capacitance in terms of farad, what you should do is find out how many micrometers you have. As long as you find how many micrometers you have, which is basically the width. We talked about the width and the relation between the width and the capacitance in the previous video. So if you found the width, you find how many micrometers you have. Simply multiply it by this value, which is given by every generation, and you can get the capacitance. If you have next generation, like still, both of them are old, but this is actually older. This is a 65 nanometer. It has 1 femtofarad per micrometer. Now, if the width, which is the critical components that we need to calculate, if the width given in lambda is represented by the letter K, and you find out how many lambdas, what is this width for every transistor, then if this width increases, then also the capacitance increases. We said before that this capacitance is equal to C per micron multiplied by the width. And the C per micron is this value for 0.6 and 1 femtofarad per micrometer for the 65 nanometer. Great. So I need to find K. I need to find the width of any transistor. If I find the width, then I can find the capacitance simply by multiplying with the value that were given to me for every generation. Now for the resistance is like approximately 10 kilo ohm times micrometer in the 0.6 micrometer, like comparing this one to the same one over here. So this is both in 0.6 micrometer. The resistance is 10K, and here the capacitance 2 femto. By the way, femto is 10 to the power of minus 15, if you don't know. That's the letter F, the small f, 2 femtofarad. Now, if you have this generation, the 65 nanometer, then there is a reduction in the resistance, only 1.25 kilo ohm times micrometer. Now, if the width, again, we will talk about the width. There is a relation between the width and the resistance. As you increase the width, if the width lambda, which is again represented by the letter K, as it increases, then the resistance decreases. And to understand this better, imagine you have a pipe, and the pipe there is like water running through this pipe. If you increase the diameter of the circle of this pipe, which is basically a cylinder, but the circle is increased in diameter, this means that you are increasing the width. And as the width increases, then the resistance, like the water have more space to run, the resistance will decrease. Now, for a unit transistor, we say that the inverter has a ratio 1 to 2, and also you could write it 4 divided by 2 lambda. This would be the length, and this would be the width. The length is the the length of the poly. And remember the poly or the red lines that we draw in the stick diagram and the layout, they are always 2 lambda. They never change. But the width change based on the connection that you have in the transistor. Do you connect them serially? Do you connect them vertically? Serially or in parallel? This makes a difference. To understand this better, let's model the resistance and the capacitance in the transistor themselves. In both the NMOS and the PMOS. So in the NMOS, if you find the width of transistor, which is K, you would say that I replace this transistor by 3 capacitance for each one of the terminals, for the D, for the S, and for the gate. You have a capacitance here, another capacitance here. What's the amount of the capacitance? It's the same width, which is K times C. What is this C? Is the one value that will be given to you, which is the C per mile. Now, what about the resistance? So the resistance, if you know K, then you can replace the transistor by a single resistance and a switch. The switch indicating the really operation of the transistor, whether it's on or off. So this resistance, the amount of resistance is R over K. R over K. Now, if we do the same for the PMOS, you would say that similarly we can do the same for the capacitance, but the capacitance now are connected to VDD. Here it's connected to the ground in the NMOS because the NMOS in the pull down network. And if the pull down network have a path to the ground, then all the capacitance should be discharged. This is why they are connected to the ground. For the PMOS, all these capacitance will be connected to VDD because they are in the pull up network and they are connected to VDD and they need to be charged. So now the amount of the capacitance is the same amount of the capacitance. You deal with them in a similar way, whether it's NMOS or a PMOS transistor. So first find what's the value of the K for this PMOS. Now for the resistance, there is something that you need to be or remember all the time. For the PMOS, now the resistance here is 2R over K. Here it's only R over K. But the resistance here is twice that amount. So why the resistance of the PMOS is twice the resistance of the NMOS given the same width K? Same reason that we talked about before many times. It's because that by inheritance, the mobility of the electrons, mu n, is equal to twice the mobility of the electron, meaning that there is more resistance. This is actually twice the resistance in the PMOS compared to the NMOS. Now, to put everything in perspective, this is what you should always remember, that the resistance in the NMOS, if it is R, then the PMOS, it's twice the R. Now, what we want is how to find K. How to find the value of K for each transistor. Or we can say it in another way, how to size the transistors. We have a target here. The target is to make sure that the pull-up resistance, RP, is equal to the pull-down resistors, RN. And to do this, if you have transistor here and another transistor here with a certain dimension, you have the length, the width, and also you have the thickness. Then notice that here, if you want both of the resistance equal to each other, then you make the width of the P twice the width of the W. And this is what we talked about before, that the ratio between the N and the P for a simple inverter is 2 to 1. 2, 2. And this is actually the now for the inverter, it's very easy that to conclude that the value of the the width of the NMOS is equal to 1, and the value of the width of the PMOS is equal to 2. Now, to make this clearer to you and to find out the reason why we are caring about having the RB equal to the Rn, let's look at this. If the RB is equal to the Rn, then if you are looking at the output Y and the inverter, and every time you are changing the input to change the output and make it swing between 0 and 1, let's say that in the output you have 0 and then followed by 1, 0, 1, and 0, and so on. If the resistance in the down or the pull down is equal to the resistance on the pull up, this means that the charging and the discharging take the same amount of time, which means that the rising time when you are charging is the same. It will take the same amount of time as the falling when you are discharging. Similarly here, and it keeps swinging in a very symmetrical way. Now, if they are not equal, then let's say that you make them the same. Let's say make them 1 and 1. So you didn't take into account the mobility, and you didn't increase the width of the PMOS and make it twice the NMOS. If the ratio is 1 to 1, what will happen is now the charging will take more time because it's facing twice the resistance if it is 1 to 1. And this is what will happen. The charging will take a lot of time and the discharging will be faster compared to that, and so on. Now, which one, if you were asked which one you are preferring, then clearly it should be this one. Now, to find R is equal to L divided by W times R squared. And the R squared is actually the resistivity rho divided by the thickness T. T is what is indicated here. This is the thickness, and rho is actually based on the material of the used in the transistors. It's given value. It's a given value based on the material. So you, for example, you have resistivity for any conductor: gold, silver, aluminum, copper, and so on. And you also have resistivity rho for certain diffusions, for the polysilicon and so on. So now this is the equation dominating or to find any resistance. Now we have Rp, where you have this index P everywhere, and you have Rn, where you have N over there. Notice also that the resistivity rho divided by the thickness is actually what we call the R squared. R squared. So if you have a certain R squared, you just count how many squares you have, indicated by the value of L and W. So if you divide L over W, you have how many R squares in the total resistance, which is R. So now the goal is to make RB equal to Rn, as we said. To do this, what we will do, we'll take the RB value and the Rn value, and we'll substitute the right-hand side for each one of the equation over here. Now, we know that the R squared of B is twice the resistance of the N, because the mobility of the N is actually twice the mobility of the P. So what we are going to do is we will substitute one for the other. So here we take out the R squared of the B out, and we take in its value and we plug it here. This is what we have. And from this, you can say that you can cancel the R squared of N, and you end up with this equation, 2LB over WB equal to LN over WN. And now we will do some simple mathematical manipulation, and we will make the WB in the numerator, the LB in the denominator. And there is a reason for this, because usually what you do is you are assuming the value of Wn, and then based on the Ln that you have for the N and the B, you can find the WB. So usually you have this, and you want to calculate WB. This is why we given you this value. And this is a key result. So we repeat it again here. And we know in the inverter, we said that it's 2 to 1. You can see or you can say for the simple inverter. Now we will calculate the 1 and 2 using this mathematical equation. So for the inverter, the pull down, first you assume, you would say that the Wn is equal to 1. So now you know the value of Wn. Now to find WP, you will apply this equation. So you say, okay, I know this value. I said it's equal to 1. Now the Ln and the Lp for the inverter, it's indicated by this layout that it's the same value. This is the Lp, and here is the Ln. So Ln and Lp, they are equal to each other. So you can take them out, and you said that the Wn is equal to 1. So WB is 2 times 1. These are canceling each other, and the WB is equal to 2. So to have the same resistance in the pull down and the pull up, the ratio must be, if you assume the Wn to be 1, then WB must be 2. If this is 4 lambda divided by 2 lambda, then in the pull up, it's 8 lambda, which is twice that, divided by 2 lambda. 2 lambda being the length, and the 4 and the 8 being the width of the NMOS and the PMOS respectively. So this is for the inverter. And the inverter, to be honest with you, that's it. You can always remember this. It's 1 to 2. That's the how to size the transistor and the inverter. But what about other gates? What if you have another circuit that is not an inverter? What to do with that? So to size any other gate, it's compared to the inverter. What we do is we compare always against the inverter. All the resistance in all paths must be equal. That's the idea. We try our best to make them equal. Sometimes you can't, but in the beginning, this is the assumption. We want all the paths to be equal, and you size based on this intuition. Now, count how many transistors in series in the longest path to the ground or to the VDD. And from that, you find the value Q, which is how many series that I have in the longest path on the ground or the longest path in the VDD. And then you balance the other paths based on the value of Q. How? First, let's figure out the pull down and then the pull up. The pull down, remember, what we are doing is we are comparing to the inverter. So you'd say that the Wn of your gate, your circuit, divided by now the value of Q, which is the series, is shown down. Q times Ln is equal to the value Wn of the inverter divided by 1 times Ln. Why 1? Because you have only one transistor in the pull down network connected to the ground. And from that, you can cross the Ln with the Ln, and you will end up saying that the Wn of the new circuit is actually Q times the Wn. So you would say that the inverter has 1. How many series I have in this new circuit? I multiply it by 1, which is the inverter. That's the sizing of any other gate if it has a series. Now, for the pull down, what are you going to do? Similar thing. We compare this to the inverter. So in the inverter, we have the WP gate, WP inverter. We have the LP. Now it's multiplied by Q based on this, how many series you have in the pull up network. So what happens? You cross this with this, and you end up with the same equation, whether you have Wn or WNP. So you compare the pull down to the pull down of the inverter. You compare the pull up with the pull up of the inverter. But remember, the ratio is 1 to 2. We will try to apply these rules, and we will do it in a quicker way with more examples throughout the class. So let's start with this very simple example. If you are giving this question, estimate the delay of a fan out of one inverter. Fan out of one inverter, it means that you are having an inverter fanning out to feed another inverter. So you want to find the delay of Y. What's the delay of this inverter? When I say what's the delay of a circuit, let's say it's a black box. It has certain inputs. It has certain outputs, or maybe a single output. What I mean by the delay is what is the delay at the output? What's the delay of this point to have its value from the input to the output? So I'm interested about this point. And this is the point that I'm interested on. Now, to calculate this, we will do it slowly by applying the model, so you understand what's going on. So what happens, I know the inverter is 1 to 2, and we discussed this. This is the way I size the inverter. Now, this means that we need to find the delay when Y swings to 1 and when it's swinging to 0. It doesn't matter which one do you choose, swinging to 1 or swinging to 0. The reason is we actually did the sizing. So if you go swinging to 1, means that you are charging, it will take the same amount if you are swinging to 0, which means that you are discharging. So what will happen is I will take each transistor and I will try to plug in its model. Remember, if I have the transistor, I have 3 capacitance and 1 resistance. So what happens, this is what I will do. Now, for this, remember, the point of interest to me is Y. Now, in the Y, I have this 4 resistance or 4 transistors connected to the Y somehow. The Y is connected to this transistor in this part. It's connected here. It's also connected to the gates of each of the transistor on the other side. So what happens is I will take this transistor and I will plug in. It's 3 capacitance. There is a capacitance also here and a single resistance. Similarly, here, 3 capacitance. There is also another capacitance here, and there is a resistance. This capacitance and this capacitance is ignored. Why? Because the input, and this is our assumption all the time, is there for a very long time. So I don't have to wait any second for charging this node, the input. So there is the capacitance there, and the gate doesn't affect it. Only in the initial inputs, the first inputs, which is A here. This is why I don't put it here and there. What do I mean by there's supposed to be a resistance here? Remember the model that we discussed here, that any transistor, InMOS transistor, is replaced by 3 capacitance and 1 resistance. Now this one I crossed in the example. Also, I could cross this one and this one. And the reason is because it's actually VDD in one terminal and another VDD in the other terminal of the capacitor, which means that this one doesn't need time. There is no voltage difference between this capacitance to be charged or discharged. Similarly, so I also can ignore them. The one that really matters to me is this one and this one, which is basically the one that's connected here and also here. Those 2 capacitance in those 2 diffusions is the one that matters to me. Now, how to find its value? Why did we say 2C and C? The reason is our sizing. We say that the K here is 2, so it's 2C. The K here is 1, so it's 1C or C. Now for the resistance here in the NMOS is R over K. K is equal to 1, so it's R. Now for the resistance in this one is 2R over K. And the K here is 2, so 2R over 2 equal to R. 2R over 2. So it's equal to simply R. And also it's indicated by, we actually made the size and to make the resistance equal to each other. This was the goal. Now, what about the other capacitors? Now, again, our point of interest is this one. And now here it's connected to the gate here and the gate. Remember the capacitance that we ignored in the first two transistors? Now it's showing in these two transistors because you are connecting the Y to the gates. So you have 2C here and you have C over here. Now, for simplification, we could say the following. That this point Y, which is this point, I could be either discharging or charging this node. We will assume that discharging whenever we can. So if I assume that I'm discharging, it means that I'm going through this resistance to the ground, which means that this path here is on and the path over here is off. Because this path is off, I can cross everything there in the top. So this is not there, the resistance is not there. Only this resistance, I assume, and I assume these four capacitors. These four capacitors, as shown by here, you can say that these are in parallel and you can sum them up. Those also in parallel and you can sum them up. But to make things easier for everybody, we would say that you can assume that all these capacitors are actually in parallel. And this is to make our life easier. And you can add them up together, which is basically 2C, 2C, C, and C. The total is 6C. And from that, we can get the delay. The delay would be the resistance R time the amount of capacitance that you add together, which is 6C. So the delay is D is equal 6RC. In this example, I explain it to you in detail, but you can get actually this result quickly, really quickly. Now, you know that this is your point of interest. It's connected to this point, this point, this point, and this point. Assuming that you need to discharge this point through the ground, then you need to empty every one of these capacitors, assuming the worst case that they are full of charge, which means you will add them up. 2 plus 1 plus 2 plus 1, which is 6. 6C times the resistance that you are going through, which is R. So it's 6RC. So you can get from here directly, you get the delay without doing the model, because this is a simple inverter example. Let's take another example, which is the 3-input NAND circuit. Now, you are asked to sketch a 3-input NAND with transistor width. So you need to find the width of each transistor. Given that this is your target, you chose to achieve effective rise and fall resistance equal to a unit inverter R, which means that if you have the unit inverter, you are comparing against it, and you want the resistance of the pull down equal to the resistance of the pull up. How to do this side? Now, I will do it quickly, and also I will apply the rule. They are both the same. But I usually do it this way because if you do the same, you always keep thinking about the circuit, and if there is differences, you can manage the calculation. So what happens, you would say, I will start with the pull down, okay? If I have only a single transistor connected to the ground, then it will have the same sizing. But since I have 3 in the series, this means now I need to multiply by how many transistors I have, which is the Q that we mentioned. We mentioned the value of Q, which is how many amount of the series going to the ground. So there are 3 transistors. We have it 1 here. So you would say that you have 3, 3, and 3. This is the sizing that you have for each one of them. You make the width of this one and this one and this one the same. All of them are 3. Now again, do the same thing for the pull up. You only worry about how many transistors you have in series to the VDD. So you have only one in this path and only one in this path. You can pick any. So if we pick this one, then we would say it will have the same amount of the width of the inverter in the pull up. So if there's 2, then here is supposed to be 2 for each one of them. And by the way, if you have transistors that are parallel, they will have the same size. And basically what we did here is this. We applied exactly what we've said. So the Wn is Q times Wn of the inverter, which is Q now is 3 times the Wn, which is 1. 3 times 1 is equal to 3. This is what we have, 3, 3, 3, and the pull down. For the pull up, we say, again, we have only 1 to the VDD. So Q over Q is 1 here. And the WB of the inverter is equal to 2. 1 times 2 is equal to 2, and this is what we have. You can do this in your head, as I explained to you, without looking at or writing out the mathematics. Or you could, if you feel safer if you apply the mathematics, apply. So and now we have this sizing. So the next, you were asked to annotate. So write down the 3 input NAND gate with the gate and diffusion capacitance. So find the diffusion capacitance, find the gate capacitance for each interesting node. We said that the node of the VDD here, since it's always connected to the VDD, and this node here is connected to the ground, we don't have to consider their capacitance. There is no, they won't take any time from you, so don't worry about these connection for the capacitance. The sizing we already put them. The first important node that you care about is the output. So now the output, the capacitance here is, look at where is the connection from this point everywhere in all the transistors. So you are connected here to 3, to 2, to 2, and also to 2. Adding 3, 2, and 2, and 2 equals to 9C. So we have 9C here. This is the capacitance. Now, what about, we said this node, we don't have to calculate the capacitance on it, or this node that is connected everywhere. We don't have to do it. Now, what about this node and this node? This node, since the diffusion here is shared, we would say that it's equal to 3C. Similarly, this one, because the diffusion capacity, the diffusion is actually shared over here, then the capacitance is only 3C. What about the gate? What about this node and this node and this node that is connected for each gate? It's connected to 3 and 2, so we say that it's 5C. Similarly, here it's 5C. Similarly, here it's 5C. So you always follow the point and add up the sizing to find out the capacitance, whether they are the input, the gate capacitance, or the diffusion capacitance. But be careful of these points, or you'll always assume that you have shared capacitance. You don't add them up. You don't add 3 and 3 and you say 6C. No, you don't add them up. They are shared, so it's only 3C. And this discussion that I just made with you, this is exactly what we are drawing here. It's 9C, 3C, 3C, but now we draw the capacitance themselves. So we annotate all these information, important capacitance information. The resistance, we don't have to write it down up to this point. We will first introduce to you the Elmore delay model. Why do we need the Elmore delay model? Let's go back first. Can you add up these capacitance together? Were they parallel like the inverter example and we add them up together and that's it? No. each capacitance is a little bit like not directly related or connected to the other capacitance. There is always a transistor between them. Or this capacitance here, it's actually connected to the gate and there is no current flowing through the gate. So we need to deal with these capacitors. And the simplest way to put them and to put them all together in one model is using the Elmore delay model, which is called the RC ladder or the RC delay model, or some people call it the Elmore delay model or Elmore ladder. There's many ways of saying the same. It's basically, you will have baths for each capacitance. If you say that you are connected to the ground and you want to discharge these capacitors, so you would say, okay, I will discharge this capacitance first. It will take some time from me. And then I will discharge this capacitance, and then this one, and then this one, and so on. So indicated by this, you have how many capacitance you have. If they are Cn, then you will have n different paths that you need to worry about. So you calculate for each path, for each specific path, the capacitance, how many capacitance you have, times the resistance. So for example, the first path here is the C1 times R1. Now for the next capacitance, C2 times R1 plus R2. For the next path, it's C3 times R1 plus R2 plus R3, which is supposed to be somewhere here. And the last one, Cn, is adding up all the resistance in the line times this capacitance to be able to discharge it. So simply, you multiply the capacitance that you want to discharge. Usually, we take the discharge path. If you want to take the charge path based on the question, then you can say that's the charging path. So you take this capacitance and you multiply it by the resistance in that path, from I all the way to the source, whether you are going to discharge in the ground or charging to the VDD. That's basically the Elmore delay model. Let's apply this delay model to our circuit. So we said this is what we reached, sizing 333, 222. This is the 9C that we said. And here we have the 3C in this point and this point. We call it N1 and N2 and Y for better explaining the problem for you. Now we added a little bit more. We say that estimate the worst case rising and falling delay for this 3 inputs NAND driving each copy of identical gates. So it's connected or it's fanning out to each copy of itself. And by the way, in this example, it's connected only in a single input of these 3 inputs. So it's only connected to one of the inputs, the first NAND, of the second NAND, of the third NAND, and up to the H NAND gate. And because of this, you would have in this node 9C that you are looking in this direction as the output capacitance, and also a certain amount of capacitance looking at the gate of the other H copies of NAND circuits, which is basically 5C. We calculated the 5 because they are the same circuit. So we calculated the 5C coming to the gate. So it's 5C multiplied by H. 5C multiplied by H. So this node, the total capacitance, they are in parallel. You can add them up and you say 9 plus 5HC. This is the capacitance in the node 4. Now we put the problem all together in one design. Now, let's try to find the worst case rising and the worst case falling delay of this circuit. So this is the point of interest, the Y. And you will say, okay, let me start with the rising. You are rising. So I would say, okay, I need to worry about this capacitance, which will be this one. This capacitance, the 9 plus HC, I need to, it's rising, so you need to connect it to the charging path. So now the resistance here, R, is equal to 2R over K, and our K is equal to 2, so it's simply R. And the capacitance we already calculated. So you would say, okay, that's a very simple path. It's only a single path going to the source, which is this one. This capacitance multiplied by this resistance, 9 plus 5H times RC. This we would say that this is the worst case propagation or rising propagation field. Now, is that really the worst case? The answer indicated in the slide, no, it's not. Why it's not? You didn't consider every possible combination. To solve this problem and to make sure that you are getting the worst case scenario, let's see what's going on in this design or this net. To get the worst case delay, consider all the three inputs starting from 0, 0, 0 all the way to 1, 1, 1. The truth table, which is 8 possible combinations. But we are not machines, we are humans and we have brains. We have a brain, so we can get some combinations that we know that this will be the worst case. You can't say that the worst case in the rising if you have 1, 1, 1. If you have 1, 1, 1, then this means that this is on, this is on, this is on, and this one is off. So there is no path at all coming to the VDD. So 1, 1, 1 definitely is not going to give me the worst case delay. Also, if I say only I have one path here in the pull up that is closed, and 2 of them are on. So this is not the worst, because if you have 2 paths, then you are actually charging faster. You are charging this node faster. So the worst case would be that you have 1 path is on and the other 2 paths are off. And you have 3 scenarios in this situation. Either this is on and those off, or this is on and those off, or this is on and those off. These are the 3 scenarios. Now, from these 3 scenarios, which one will give you the worst case scenario? The worst case is given by this one, which is when this is off, and this is on. Why? If this transistor is on, then definitely this one is off. If those 2 off, then definitely both of these transistors is also on, which means that you are not charging only Y, you also need to charge N2 and also N1. And that's the worst case that could happen when you are charging this gate. You have 3 nodes that you need to worry about. These 3 nodes indicated by this model. The first one is 9 plus 5 HC, and you have the resistance R that you already have. The second path, which is from N2, is 3C, moving through this resistance here, and then another resistance here. Now, what's the value here? The value here, we find it, it's R. The value here is R over K, and the value of K is equal to 3, so it's R over 3. Similarly, for N1, you have 3C, and you are moving through 3 resistance now, which is R over 3, and R. Now, you could apply the Elmore delay model or the RC ladder by discharging each one or charging each one of these capacitance to the VDD or charging it by the VDD. So you have 9 plus 5 HC going through one resistance. You have the other one, which is this 3C going through two resistance, R plus R over 3. And the last one going through 3 resistance, R plus R3 plus R over 3 plus R over 3. And we got this by checking all the input combination from off to on with some intuitions because we are smart, let's say. Now you can simplify this, and you should always simplify by finding what is the amount multiplied by R's. So, because if you find the R and the C, if you are giving this value, let's say that you have the C 2 femtofarad per micrometer, and the R is, let's say, 10 kilo ohm times micrometer, then you can multiply those together. Then the micrometer will go away. I'm talking about the unit, and you will end up with only ohm times farad, which is basically second. And this is unit of the delay. So that was the worst rising propagation delay. What about the falling delay? The falling delay, it has only one case and one case only. And this is when this is on, and this is on, and this is on. Because you need a path to the ground to discharge. So it's on, which means those three are off. So you worry about Y, N2, and N1, indicated by 3 resistance. Each one of them has a value R over 3, R over 3, and R over 3 with the same capacitance. So you can see that we apply again the ladder, which is 9 plus 5 HC times those 3 resistance, the addition of these 3 resistance, which is R over 3 plus R over 3 plus R over 3. I know that the total is R, but I show it to you so you know that I'm talking about this here. Similarly, the second path over here, which is 3C times R over 3 plus R over 3. And the last one is 3C times R over 3. And you can simplify this, and you find that it's 12 plus 5H times R. Now compare the rising to the falling. These are the worst case. Even though we try to make the sizing of the transistor such that the rising, the resistance in the falling and the rising are equal, the delay at the end of the day, they are not that. They are not. You can see that this is 18, that this is only 12. So there is slightly some difference between the amount of the delay in the rising and the falling, but at least we are going or heading to a good estimation. Now, if you were asked about the total delay, usually when you have a circuit like this one, you would say, okay, what is the delay? What's the delay of the Y to show up? What is the amount of the delay? I give you one number. I don't give you two numbers, the rising and the falling. Usually you get only one number. So to have this or to do this, you just simply average them. And you know that the midpoint between the 12 and the 18 is 15, and this is the average. Now, it's good to talk about some of the leftover subjects before we finish this video. First, the delay components. Know that you always have output capacitance or the diffusion capacitance, and you also have the gate or the input capacitance. The output capacitance in our example was the 9C. Well, the capacitance was the 9C. The input capacitance was the 5HC. That was the capacitance, that the capacitance number, which is this 9 and C. Now, again, we could do the same, or we extend this to the delay. So we have parasitic delay, or the output capacitance, diffusion capacitance. Also, it's called the parasitic capacitance. So we have a parasitic delay, indicated by 9 RC. It's always independent of the load. Like if you have the NAND not connected to anything. And we also have, against the gate or the input capacitance, we have what we call the effort delay. So how much effort is this gate is doing when it's connected to other gates? So it's proportional to the load capacitance that you are connected to. These are the delay components, and we explained them in the previous example. Basically, just to make it short, the output capacitance or the parasitic delay, you look at it from this direction, and the gate capacitance or the effort delay, you look at it from this direction. Now the contamination delay, which is the best case, the shorter delay, which is the best case. So in our example, if you were asked about what is the best case falling delay. So the best case falling delay, we have only one path. When this is on, this is on, this is on, and those three off. That's the only path that we can have. And that's why the best and the worst falling delay, they are the same for this thing. But what about the pull up or the rise? The best case rising delay for this circuit, if we have all the paths are connected to the feeding, meaning that this is on, this is on, and this is on, and that there are three, all of them are on, then this is off, and this is off, and this is off. We don't have to consider this 3C or not this 3C. We only consider the 9C plus 5HC. Not only this, you have three paths that you are can choose, or from these paths, it's actually charging much quicker than if you have only one path. This is indicated by the parallel resistance that you have here. We say that it's R over K. So, 2R over K. So 2R over 2 is only R and R. This is the parallel resistance. We have R, and we worry about this capacitance, which is 9 plus 5HC. From your study and basic electrical courses, the parallel capacitance, if they have the same amount, then the total capacitance would be R over 3, only if they have the same amount of resistance. The rule that you used to have long time ago maybe is 1 over R total is equal to 1 over R1 plus 1 over R2 plus blah, 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 plus 1 over Rn. So you add those together, and then you flip them back to get the R total. And from this, we can apply it here. You would say that 1 over R total, the one that we are interested on, is 1 over R plus 1 over R plus 1 over R, which is equal 3 over R. You flip and you get the R total equal to R over 3. So you have only one path, which is 9 plus 5HC times R over 3, which is basically this amount. And this is the way you get the best case delay. You also need to know that we have some simplification. For example, remember that we say here that the capacitance is 9C because we add 2, 2, 2, and 3. But if you draw the layout, you would find that you have only 3 connections. One below, let me change the color. One below here in the pull down, which is indicated by the 3C, which is this one. And you have this one, which is on the edge, basically is this one. And those two is actually shared together. So you have only one of them. So it's 3 plus 2 plus 2, which is 70. In reality, it's 70. But if we consider this detail, then for each gate, we need to draw the stick diagram or the layout to indicate the correct amount of output capacitance. To make our life easier, we don't going to consider this. We would say that it's simply 9C, like what we explained in the example before. But you should know that you should be aware of this fact. Now, the only reason is that because we have shared contacted diffusion over here. Now, if you were asked, which layout is better? This layout or this layout? This is a stick diagram, actually. This stick diagram or this stick diagram. Which one is better? You know that they are equivalent in functionality because you have two series here and you have two parallel in the pull-up. We did the parallelism in a different way from here to there. So we notice that now we know that we need to worry about the output. Here, the output is connected to one term, one contact here, and a single contact here. So two contacts here only. The output here is connected to three contacts. So we have three capacitance that we need to worry about. Here we have only two capacitance, and one of them is shared. And because of this, we know that this one is better than this stick diagram. Also, you could look at it from the other way around, is by looking at which contact is connected to VDD. So now we have two contacts, two diffusion are connected to VDD, always charged, always ready. We are not spending any delay on them. And here we have only one of them connected to VDD. And for the same reason, we have this design better than this one. And this marks the end of this lecture. And for the next video, we will talk about another way of estimation the delay using the logical effort.